The introduction of this scientific paper discusses the challenges in discovering emergent morphologies in the directed self-assembly (DSA) of block copolymers, BCPs. While DSA is a powerful technique for creating complex nanostructure arrays, finding the appropriate morphologies based on changes in polymer architecture, composition, or assembly constraints is difficult due to the high dimensionality of the design space. The authors propose a machine-guided approach to autonomously discover emergent morphologies from a cylinder, lamelli BCP blend directed by a chemical grading template. This approach allows for the mapping of the morphology template phase space in a fraction of the time required for manual characterization and identifies areas that require further investigation. The authors demonstrate the localized, template-directed partitioning of coexisting lamella and cylinder-like subdomains at the template period length scale, resulting in previously unknown morphologies such as aligned alternating subdomains, bilayers, and a ladder morphology. The introduction highlights the trade-off between complex organizational information and the use of more complex building blocks or constraints in self-assembly. Blending BCPs with other polymers or nanomaterials, or layering BCPs with different domain sizes or morphologies, can overcome this trade-off to some extent. Directed self-assembly (DSA) techniques, such as epitaxial registration of BCP domains to templates, allow for local control over chain distortion, domain orientation, and pattern transferability. However, these approaches introduce their own complexities in terms of process control, template design, and composition selection. The authors emphasize the need to efficiently explore the high-dimensional parameter spaces and discover the underlying principles that govern assembly motifs. The authors previously demonstrated the use of a responsive blend of BCPs to selectively enhance and control nanopattern complexity in DSA. They used a 1-to-1 blend of cylindrical and lamellar D-block copolymers to form coexisting line and dot patterns. By adjusting the grading template pitch and/or line width, they were able to locally select between line and dot patterns. However, the prior investigation was limited to a narrow range of template parameters, and more complex assembly behavior, including three-dimensional morphologies, may be possible as the template parameter space is widened. In this study, the authors investigate the assembly of the same BCP blend on chemical patterns with a wider range of line widths and pitches, including pitches that are more than 2 times the equilibrium self-assembled spacing. To overcome the challenges of manual characterization and analysis, the authors autonomously probe the system using synchrotron X-ray scattering. They systematically map the self-assembly behavior across the entire chemical pattern space in multiple quantitative dimensions, revealing unusual 3-dimensional morphologies. These morphologies exhibit local partitioning into cylinder-like and lamella-like subdomains, depending on the chemical pattern dimensions. The authors highlight the significance of their findings, as the observed ladder, skew, and alternating morphologies have not been reported in previous studies. They suggest that the combination of combinatorial sampling and autonomous characterization holds immense potential for accelerating the discovery of designer hierarchical self-assembled morphologies. B depicts the schematic of the autonomous small-angle X-ray scattering (SAXS) measurement, where the X-ray beam is focused to a small spot on the sample to avoid averaging across adjacent patterning fields. The autonomous SAXS measurements were performed at the soft matter interfaces beamline at the National Synchrotron Light Source 2. The figure also shows the workflow of the machine-guided selection of subsequent measurement locations within the pattern array using a Gaussian process, GP, regression method. The figure presents a map of scattering prefactor intensity, P, as a function of lambda and W, showing the emergent morphologies within the design space. Exemplar SAXS patterns and corresponding scanning electron micrographs, SEMs, are provided to illustrate the different pattern types dominant in each region of the design space. The different pattern types observed include self-assembled line, hexagonal or line, isotropic, skew, and alternating cylinders and lamellae or ladder patterns. The scattering prefactor intensity map reveals distinct regions of high intensity associated with different pattern types in the design space. This figure shows the weighted contributions from specific pattern motifs within the template design space based on the fitting of the azimuthal scattering data. The intensity maps represent the presence and dominance of specific pattern motifs, including isotropic, line, hexagonal, skew, and ladder patterns, in different regions of the design space. Exemplar SAXS patterns and SEMs accompanying the intensity maps demonstrate the characteristics of each pattern type. The figure depicts the variation in the azimuthal angle of maximum SAXS intensity, chi-C, across the template design space. The map of chi-C shows a continuous variation in the region identified with the skew morphology. SEMs obtained from selected locations within the skew region reveal dots on a hexagonal lattice, connected by lines at angles similar to those of chi-C measured by SAXS patterns. The figure also presents a schematic of the proposed bilayer morphology responsible for skew patterns and the complex morphology that emerges at larger lambda values. The SEMs validate the proposed models for the skew and complex morphologies. This figure illustrates the emergent patterns in proximity to lambda approximately equals 2L0. It shows the schematic unit cell and SEMs of alternating cylinder-like and lamella-like subdomains aligned along the grading direction, which emerge in the vicinity of lambda approximately equals 2L0 and larger values of W. The figure also depicts the schematic unit cell and SEMs of ladder structures, which emerge in the vicinity of lambda approximately equals 2L0 and smaller values of W, or in regions where lambda is slightly more or less than 2L0. The SEMs provide visual evidence for the presence of alternating and ladder morphologies, confirming the proposed models. The figure presents an exemplar coarse-grained molecular dynamics (MD) simulation result for a cylindrical, lamellar block copolymer (BCP) blend on a chemical grading template. The simulation results show a remarkable agreement with the experimentally observed alternating morphology in the vicinity of lambda approximately equals 2L0. The figure also provides a plot of the local fraction of cylindrical minority BCP chains, showing the enrichment of cylinder-like chains near the substrate between grading lines. These results strongly support the hypothesis that localized chain enrichment plays a crucial role in the self-assembly of the observed morphologies. The authors of this scientific paper discuss the characterization of complex three-dimensional morphologies that emerge through self-assembly of block copolymer blend thin films in response to underlying chemical pattern templates. They use synchrotron X-ray scattering to map a combinatorial sample, expanding the parameter space and providing morphology descriptors without human intervention. The autonomously derived results guide electron microscopy characterization, revealing previously unknown morphologies and helping to distill general principles of subdomain partitioning for predicting and designing patterns. The authors highlight the significance of their work in engineering hierarchical self-assembled morphologies with precise registry control. They also emphasize the value of their autonomous characterization approach in understanding complex assembly behavior and freeing human experimenters to focus on interpretation and hypothesis formulation. They provide detailed information about the materials and methods used in the study. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.